Welcome to another video from Roland Mösel, founder of Planetary Engineering Group Earth. Floor heating and or wall heating. This is the question today. Let's start with the experiment. First we make a floor. Now you wonder maybe why so warm below the floor, 15 degrees Celsius. This is because below the floor is a low temperature heat storage. And this low temperature heat storage, this is covered in another video from me about 3 patents around the heat pump, has typical 15 degrees Celsius. Now this floor emits towards the indoor room 3.21 watt per square meter and to the bottom 1.24 watt per square meter. Now the wall, the unheated part of the wall. Parts of the wall are unheated because the outside area of the wall is bigger than the inside area, and so parts of the wall are not heated. In this case we take an outdoor temperature of -5 degrees Celsius and we lose per square meter 2.98 watts. Now the heated part of the wall. The thermal loss to the outside increases to 3.36 watts per square meter, and towards the inside we have 7.48 watt per square meter thermal loss. The ceiling is very simple. 2.68 watt per square meter thermal loss. Now this is the house for the experiment. It's about the same size as the GEMINI next generation house, but the wall design and other designs are not identical with GEMINI next generation because I consider a patent about the wall construction, so I cannot publish here the real wall construction, but only a thermically similar wall construction. This is 10.4 meters times 7.6 meters and the height is 3.1 meter. Now we go to the thermal balance. For luck, we have a very good heat recovery from exhaust air, so the 120 cubic meters per hour of air exchange take only 148 watts. We have the big ceiling and this loses 211 watts. And surprise, the windows even emit more. They are very good windows. U value 0.8. This means per square meter and per degree temperature difference is only 0.8 watts to lose to the colder side. But 270 watts. Now the heated part of the wall emits 237 watts towards outside and 527 watts towards inside room. There's also a small part of the wall not heated, and the floor emits 77 watts towards the low temperature heat storage below and emits 198 watts towards the indoor room. We have a total of 1039 watts of thermal losses, but the emission of the heated wall and floor together are only 725 watts. This is because this emission of thermal energy has only to handle the thermal losses of the unheated parts and of the air exchange. The thermal losses at the heated parts, wall and floor, are direct handled at the emission at these parts of the house. Because we have this low temperature heat storage, I assume a temperature of 2 degrees Celsius where we shield the heat for the heat pump. We don't use it at -5 degrees, we use it at the warmest hours of the day, so the assumption is +2, and we use only 23 degrees Celsius for the pre-flow temperature of the heating system. And this gives a very high coefficient of performance of 5.64. This coefficient of performance is calculated by the Carnot formula, and it is assumed that the heat pump has only 40% of the maximum theoretical possible coefficient of performance. So only 184 watts for the heat pump. Oh, this is incredibly low, and 12 watts for air exchange. So we have a total of only 196 watts for all this house at minus 5 degrees Celsius outside. Now we make the same experiment, but without wall heating, only floor heating. In this case, we have to increase the thermal output of the floor heating to 15.14 watt per square meter. And for this, we have to increase the flow temperature of the heating system to 32 degrees Celsius. But remember, this floor is not very optimal for a floor heating alone, because we have here 25 millimeters of OSB4 plates, we have this cork, and we have this lamination on it, and so this is really not an optimal floor heating system for only floor heating. Therefore, we have also increased the emission downwards to 2.66 watt per square meter. Now the balance for the system. The floor heating has to emit 935 watts towards the indoor room, and this is done by increasing the pre-flow temperature to 32 degrees Celsius. The thermal losses are increased to 1099 watt, and the coefficient of performance of the heat pump is reduced to 4.07. And this increases the electricity demand of the heat pump to 270 watt. The other part, the air exchange, remains at 12 watt naturally. And now we make the same example with wall heating only. At wall heating only, we have a pre-flow temperature of 24.5 degrees Celsius. This is only 1.5 degrees more than at floor and wall heating together. The walls have to emit 773 watts towards the indoor room, and surprise, the total thermal loss of the houses decrease to 1020 watt. But on the other side, we have this 1.5 degree Celsius increase of pre-flow temperature, and this reduces the coefficient of performance to 5.29, and now we need 193 watt of electricity. But the differences are so small, there is no energetic reason to choose wall or wall and floor based on the energy. To use also the floor heating has only one reason: comfort. It has no reason in the energy, because it's so similar to floor and wall heating together. This is 16 millimeter aluminium pipe, and this is only 0.7 euro per meter. And when you use 10 meter of pipe for 1 square meter, it's just 7 euro per square meter. So the costs are very low, and there is no reason to use not as much heating systems as possible for the house to decrease the pre-floor temperature and to have also the wall heating, to have in summer a wall cooling for more comfort. Next, we make another experiment. A house the same size. It's not allowed in Austria because the thermal insulation is not good enough to receive a building permit. But for many countries of the world, this would be a good house, even a good example of a house. So it's not really a bad example. It's only because we want it so much better. But in many countries, quite a good house. So we start at the bottom, at the floor. You see here only 5 degrees Celsius below the floor, at the ground. This is because we have here no low temperature heat storage. There is direct to the earth below the house. And we use the Swedish bottom plate. Swedish bottom plate means we put the pipes for the floor heating direct into the concrete, and above we do only a little bit of lamination, in this case a little bit of oak, and below the concrete is ESP isolation plate, and then is the earth. And in this case, we lose towards the earth 5.96 watt per square meter, and towards the indoor room, we have to emit 41.82 watt per square meter. Oh, when you stand on this ground, you get hot feet. Yes. Now the wall of this system, we make it very, very simple. Just 30 centimeters of gas concrete, nothing else. And here we lose towards the outside 7.88 watt per square meter. The U value is a little bit above 0.3 watts per square meter Kelvin. And now the roof, and because I made the floor 25 centimeter and the roof at the other example 35 centimeter, I take the same gas concrete stones and put 5 centimeter of insulation on it, and that's all. And here we lose 5.25 watt per square meter. Now the thermal balance. I had to make the arrows in the scale 1 to 5 smaller than at the last example, because otherwise these arrows would be far too big. We have no heat recovery from waste air. Maybe the people in this house just open the window, close the window, open the window. All this theater in old houses. And so we lose for air exchange 990 watt. And then the ceiling, here we lose 415 watt. And at the windows I used only a little bit worse windows. U is 1 instead of U is 0.8 at the last example. These are very good windows. It would be better than most of the windows in houses you see around. But it's a little bit worse than the best what we have today. And here we lose 738 watt, and at the wall 773 watt, and the floor heating system loses towards the underground 368 watt and emits 2582 watts towards the indoor room. And because we have here a good floor construction for floor heating, we have only a pre-flow temperature of 28 degrees Celsius. This is a good value. But because we have no low temperature heat storage, the heat pump has to work from -5 degrees to 28 degrees. And the production of the 2950 watt of heat makes here much more electricity, because the coefficient of performance is down to 3.65, and we have 808 watts of electricity. It's more than 4 times more than at the best example. But still, remember, It's a quite good house in most countries of this planet. This is really not a bad house. Maybe somewhere it would be a good example how good a house could be. Now let's look at all the examples at heat. Quite a good house in many countries uses 2950 watt of heat. The good example with floor heating alone, 1099. This is because of much better thermal insulation and because of heat recovery from exhaust air. And the best example uses only 1039 watt of heat because of optimization of the heat system with the wall heating additional. About ventilation system with heat recovery and moisture recovery from exhaust air, I made another video. I recommend this video here. Now the coefficient of performance at the heat pump. How many watt of thermal energy you earn when you put in 1 watt. In many countries quite a good house with an air source heat pump. We have in this scenario a coefficient of performance of 3.65. This improves at the only floor heating, good example, to 4.07. This is because the low temperature heat storage increases the chilled temperature of the heat pump to plus 2 degrees instead of minus 5 degrees Celsius. And when we have also the wall heating, we can decrease the pre-flow temperature to only 23 degrees Celsius, and this means an increase of the coefficient of performance to 5.64. About heat pumps, my 3 patents about heat pumps and the low temperature heat storage, I made another video. I recommend this video here. And now the electricity for making all the heat. 808 watts at the, in many countries, quite a good house. This decreases to 282 watts at the example only with the floor heating, and decreases to incredible 196 watt of electricity at the example with floor heating and wall heating together. All this research is done for the project GEMINI Next Generation. We will disrupt the house market with an incredible new product. I recommend also this video. This was another video from Roland Mösel, founder of Planetary Engineering Group Earth, and as always, like, comment, subscribe, and hit the bell to be notified when I make my next video.